If you've ever tried to string multiple LLM prompts together, you've probably run headfirst into one of the most frustrating roadblocks in modern AI. I'm talking about the compounding uncertainty problem in multi-step agent workflows. Today, we're diving straight into a fascinating explainer on a research paper that proposes treating these LLM flows as probabilistic programs, using a brand new language called PPDL, or Probabilistic Programming Declarative Language. Here is our roadmap for today. We're going to cover 1. The LLM uncertainty problem, 2. Enter PPDL, 3. Factors and trace distributions, 4. Algorithms, IS and SMC, and finally 5. Putting PPDL to the test. Let's get right to it. Section 1. The LLM uncertainty problem. So how do we trust an AI agent when its errors just keep compounding at every single step? Right now, a single call to an LLM can be pretty amazing. But the moment you start building complex workflows, chaining multiple calls and external tools together, things get dicey. It's literally like a massive game of telephone. If step 1 is just slightly off, step 2 builds right on top of that mistake. By the time you hit step 4, you're looking at a complete disaster. That uncertainty just compounds along the whole execution trace, and you're left wondering if you can actually trust the final answer at all. Now, a lot of developers have tried to fix this using something called inference scaling. Basically, you scale up the number of LLM inference calls at test time to explore different outputs, and then refine them using constraints. You try the task a bunch of times, maybe toss in some feedback loops, and just kind of hope one of the answers hits the mark. But in practice, man, it is incredibly messy. Just picture developers pulling their hair out, writing endless spaghetti code in these nested while loops, just to force the LLM to behave. Right now, inference scaling is hard-coded directly into the application logic, which turns your codebase into this inflexible, tangled web. Which brings us to Section 2, Enter PPDL. And this is where the hero of our story enters. The whole philosophy behind PPDL is completely decoupling the search process from your core program logic. So instead of you manually coding out all those try again if this fails instructions, PPDL separates the what from the how. You literally just write your goal once, and the engine automatically figures out the attempts behind the scenes, handling all that parallel execution and inference scaling for you. It's a total paradigm shift. A traditional program gives you one rigid single output, which, let's be honest, might be entirely wrong. PPDL, on the other hand, moves us from that single deterministic output to a whole multiverse of probabilistic answers. It returns a broad distribution of possible values. From there, you can actually inspect that distribution to gauge the uncertainty, or just have the program automatically pick the answer with the absolute highest probability score. You can really think of this execution model like a branching multiverse. Each particle is basically exploring its own parallel timeline, or execution trace, through the program. The engine is simultaneously exploring all these different branches to figure out which path gives us the highest confidence. Section 3. Factors and trace distributions. To actually control these parallel universes, we have to look at PPDL's linguistic core, which relies on two fundamental concepts, sample and factor. Think of a sample as the brainstorm. It's an LLM call that introduces raw generation, data, or randomness into your program. But a factor, that is your quality control. It's a constraint you set that updates a trace's probability score. It could be a hard constraint, like a code linter throwing a strict error, or a soft constraint, like asking another LLM to act as a judge and score the output. The factor takes that evaluation and mathematically updates the probability score for that specific timeline. Section 4. Algorithms, IS, and SMC. Let's talk about the probabilistic inference engines under the hood that actually use these scores. First up, we have importance sampling, or IS. With importance sampling, all your particles, or attempts, run from start to finish completely independently. Along the way, they're accumulating these log probability scores. Then, at the very end, the engine normalizes those scores to weigh the final results. This is crucial because even if only a tiny minority of the particles actually find the right answer, those factor scores amplify the probability of the correct solutions. It basically allows PPDL to pull the right answer out from a sea of wrong ones. But then we have Sequential Monte Carlo, or SMC, which takes this to a whole new level for deep, multi-step flows. Step 1, you launch multiple parallel execution particles. But in step 2, instead of waiting until the very end, SMC actually stops at factor points mid-execution to calculate those scores. Then comes step 3, the really clever part. It resamples. It actively prunes away the low-scoring particles and clones the high-scoring ones.
Finally, in step 4, it continues executing only those most promising paths. It's like a ruthless game show where bad timelines get dropped instantly and the successful ones get cloned to focus all your compute power exactly where it matters most.
Section 5, putting PPDL to the test. So, does all this abstraction actually result in better AI agents? The data says absolutely yes. Just look at the GSM-8K math benchmark. By moving from a baseline of one single execution to SMC with just 5 parallel particles, the Granite 4 small model jumped from an 83.8% success rate to 92.3%. And we're seeing similar leaps on the MBPP coding benchmarks too. And remember, because you write the logic once in PPDL, developers can swap and test all these different models and inference engines without rewriting a single line of their core application code. But to really push the system to its absolute limits, the researchers subjected PPDL to the ultimate test, the Mini-FEF2 FR-AQ theorem-proving benchmark. If you're not familiar, AQ is a highly complex proof assistant for math, and theorem proving is notoriously brutal because literally just one hallucinated symbol can invalidate your entire proof. The goal was to see how much probabilistic inference could improve a base model on an incredibly challenging task, using the prover's own feedback as a factor. The results, honestly, they were remarkable. Using the exact same token budget, the PPDL agent running the sequential Monte Carlo algorithm solved 95 out of 244 theorems. That completely crushed the sequential baseline, which only managed to solve about 72.7 theorems on average. You can really see the efficiency playing out here, showing how SMC parallel exploration efficiently outperforms those sequential attempts. A standard baseline approach is just one particle trying, failing, and repairing sequentially over and over again. But running multiple particles in parallel with SMC, it completely proves that you need way fewer proof and repair steps to hit a high success rate than just banging your head against the wall sequentially. By cloning the good paths and ditching the bad ones mid-run, it explores the solution space so much more effectively. So what does this all mean? Well, inference scaling absolutely works, but bolting it onto traditional code is a nightmare. By treating LLM flows natively as probabilistic programs, PPDL lets us build highly complex, trustworthy agents that actually quantify their own uncertainty. And it does it all without thousands of lines of spaghetti code managing endless loops. It totally abstracts away the heavy lifting. Which leaves us with a pretty profound question. If AI can now confidently navigate its own uncertain multiverses of logic, what impossible workflows become possible tomorrow? Thanks for tuning into this explainer, and we'll catch you next time.